Hello, hi students. So this is coordination components part 9. We were looking at geometrical isomers and optical isomers, and at the end of this part 9 you will be able to understand geometrical isomers in square planar complexes and optical isomers in tetrahedral complexes, optical isomers in octahedral complexes. That is the gist of this part 9. So already we have started looking at cis-trans isomerism or otherwise geometrical isomerism. So let us look into some more types of geometrical isomers in square planar complexes. So in square planar complexes, so have a look at this one. So what type of complex is this? This is M(A2) B2 type of complex, where you can imagine A as what? Amine, and B ligand as chlorine. A type of ligands are amines and B type of ligands are chlorides, and your central metal atom or central metal ion here Pt plus 2. And so the two chlorines are adjacent to each other in the first picture. As they are close, we call the isomer cis isomer. And in the later part, the second part of the picture, the two chlorides that are green balls that you look at are with maximum separation with 180 degrees of separation results in a trans isomer. This amine and that amine, in both the cases you look at, if both amines are close, it is cis, amines are far apart. In the second picture, where the blue ball with the white balls, the blue ball is nitrogen with the hydrogens on it, 3 hydrogens on it. So the blue ball parts are far apart. So when they are far apart, we call the isomer as what? Trans isomer. This is cis trans isomer in M(A2) B2 type of complex. Let's change the ligand type. AB2, MAB2 type of complex, which means it is a bidentate ligand where the ligating site A is different from ligating site B, and still it's a square planar complex. Such example is glycinato. Glycinate is the ligand, we call them as glycinato. Bisglycinato, platinum 2 complex. Bisglycinato platinum 2 complex is what we are looking at. So in glycine you have NH2 and CH2COO minus. Glycinato ligand has NH2CH2COO minus, where one donor site is with amine nitrogen, another donor site is what? Oxygen. Another ligating site is a COO minus oxygen. So as such you have an AB2 type of complex. So in this type of MAB2 type of complexes, if in the bidentate ligand similar kind of atoms fall on the same side, have a look at the first structure. Glycinatose amine is on the top and another glycinatase amine is also on the top, which means they are close. This one and this one, they are close. Oxygen and oxygen is close. So if you try to arrange them with one variation, that you change the position of amine and oxygen, the second one you just change this one, interchange this one, then it what happens, oxygens are far apart and amines are far apart. So if they are far apart, it results in what? Trans geometrical isomer. And if similar kind of atoms are close, wherein here amines are close and oxygens are close, it results in cis geometrical isomer. So that's MAB2 type of complex, and it's a square planar complex. So as we have already seen that only square planar complexes and octahedral complexes will form geometrical isomers. Let us move on to the geometrical isomerism in octahedral complexes. Geometrical isomerism in the case of octahedral complexes of Ma4B2 type of complex, where your M is central metal, A and B indicates ligands. A type of ligands are different from B type of ligands. A type of ligands are 4 in number and B type of ligands are 2 in number. So if you try to arrange B type of ligands close to each other with a 90 degrees separation in an octahedral complex, if you try to arrange B type of ligands with a 90 degrees angle of separation, it results in cis form. If B type of ligands are arranged with 180 degrees of separation, then it results in what? A trans complex, it results in trans isomer it produces. So let us see that what are the possible ways it can be arranged. So in the first part of the picture, so have a look at B's are with 90 degrees, so it results in a cis. Again, the second part of the picture is B's with a 90 degrees separation. Here two B's are having what? A 90 degrees angle of separation. So again it is a cis. Now you change them, B here and B another here. It results in trans isomer. And B here and B here, it is also 180 degrees separation. So it's a trans isomer. Both these trans isomers are equivalent structures. They are not different. And here cis are also equivalent structures. Equivalent structures means they are completely same. Only the viewer dimension is different, but they are completely same. So that's Ma4B2 geometric isomers. Now change that. Simply instead of M, you take an example like cobalt. Instead of A and B, you take amines and chlorides. Amines and chlorides. You just try to put that and you just try to come up with some solution. In place of M, you go for cobalt plus 3. In place of A, you write NH3. In place of B, you write what? Chlorides. And try to write cis trans isomers, which we have already discussed in Werner's theory. He just tried to give in octahedral complexes cis trans isomers. So that case we have already seen. So go for keeping what? Instead of A, you write amine, and instead of B, you write a chloride Cl minus, and instead of M, you write substitute that one with a CO plus 3 and write geometrical isomers. Now let us see geometrical isomerism in MAA twice B2 complex. MAA twice B2 complex, where AA indicates a bidentate ligand with similar ligating sites, where AA indicates what? A bidentate ligand with similar ligating sites, and B is a different ligand from AA. So in total you have the coordination number 6. So it is again what type of complex? Octahedral complex, and the example we are having here is CO En taken twice Cl2 plus CO En taken twice Cl2 plus complex, which is bis ethylene diamine chloro. you should start with chloro first. Dichlorido bis ethylene diamine cobalt 3 plus ion, cobalt 3 ion you can write as. So that complex you have a look at. So how to write its cis isomer? So if two ethylene diamines are close, if two ethylene diamines are close, so here in this case they are close. If two ethylene diamines are close, then what happens? It is a cis isomer. And here two ethylene, in the second part, two ethylene diamines are what? Distant. So you can say it is a trans. Or else alternatively, even by looking at chlorides, you can say that here the two chlorides are 90 degrees separation, or with 90 degrees separation, and in the second structure the two chlorides are at 180 degrees separation. When the two chlorides are at 180 degrees separation, you can classify that structure as trans isomer. So as such, the first one is cis isomer and the second one is what? Trans isomer. So they are cis trans isomers. Even you can write that, let me so thus first one is cis and the second one is a trans isomer. Okay, so let us move to the next example, or else have a look at the ball and stick model in this case. So that's your green balls indicates chloride ions. So by looking at that, the two chloride ions are at 90 degrees angle of separation. So this is at 90 degrees, so least angle of separation. So you can say that is a cis isomer. And this is what? Ethylene diamine. This is N carbon carbon carbon, and with two hydrogen, NH2 CH2 CH2 NH2. Here also NH2 CH2 CH2 NH2. And these green balls that you are looking at are what? Chlorides. Okay, so this is a cis isomer. A trans isomer would look something like this, where chlorides are distant apart. Have a look at two chlorides are what? At what degree of separation? Here it is 180 degree of separation, and this is simply representing En. Instead of writing the whole structure, you can write En, and simply here also En you can write. So indicates what? That is ethylene diamine. So this is its trans structure. That's geometrical isomers in the case of MAA taken twice, B2 type of complexes. So here it is CO Cl2 En plus complex. Let us move on to another type of complex where geometrical isomerism arises. That is MA3B3 type of complex. MA3B3 type of a complex. So here A type of ligands and B type of ligands are equal in number, 3 and 3. Now if A type of ligands are falling on the same face, you try to arrange them in such a way that if they are falling on the same face, then it is referred as facial isomer. And if the same kind of ligands, A type of ligands, are falling on the same plane, then it is meridional ligand. Meridional plane we call that one as, and it is meridional isomer. So in the case of cis trans isomers, here it is facial and meridional. Your cis may be considered as facial and meridional is the trans form. Instead of cis trans, here we call that one as facial isomer and meridional isomers. So facial indicates that you look at this NO2, this NO2 and this NO2 are falling on the same triangular face, and this NO2, NO2 and NO2 are falling on same triangular plane. So as such, it is referred as a meridional. That's facial and meridional isomers. In the case of triamine, trinitroto, cobalt 3 complex. The next one. So here facial and meridional, how you classify them as facial and meridional, they just the write up I have given. So when the ligands are occupying are falling on the same phase, we call them one as facial isomer, and when the ligands are falling on the same plane, we call that one as a meridional isomer, or we simply call that one as mer isomer. And for facial, we write that one as a FAC. For meridional, we write that one as MER, facial and mer isomers. So just how to identify that phase and meridional. So have a look at that. So imagine one as your NO2 and one as your NH3. So blue ones are NO2 and the red ones are what? Amine, you can imagine as. So if you try to join the blue ones, you are getting a triangular phase. So then it is on the same phase they are present. So it is a facial isomer. And in the second picture, you just have a look at the second picture, second part of the picture here, this one. So in that you are getting the same plane, they are present on the same plane. The blue balls are present on the same plane. If they are present on the same plane, then we call that one as what? It's meridional plane. Meridional means it's referring to what? Plane it is. Meridional itself is meaning what? Plane it is meaning. Okay, its meaning is plane. So obviously the second one is meridional isomer, or mer isomer we call that. So that's facial and meridional isomers. In the case of CONH3 taken thrice, NO2 taken thrice, where it is a MA3 B3 type of complex, and a very good case for being considered as an important question. Sorry. So one more example here, in this case of facial and meridional with CONH3 taken thrice Cl3. So just have a look at that and identify whether it is a facial isomer or meridional. So by looking at the three chlorines if you combine, you are getting what? A triangular face you are getting. So obviously it is what? A facial isomer. So combine those three imaginarily, hypothetically. So in your imagination, you just try to make connect them using dotted lines. Then you get what? A face you will get, and that indicates that it is a facial isomer. So wherein you simply change one of its ligands position, exchange with one of the amines, change the position of chlorine with amine, then what happens? The three chlorines will fall on the same plane. Any of the amine you choose, and you just try to exchange with it. So this one you just try to exchange. So amine, instead of this amine, you just keep changing this one. If you change this one, what happens? On exchanging, you will get another isomer, that is a meridional, which would look like this. So on exchange, one of the chlorine is exchanged with amine. So on exchanging, we got something like that. So this is what? Meridional isomer. Okay. So that's facial and meridional isomers, which are geometrical isomers in the case of A3B3 type of a complex. Now the second part of this one, which is optical isomerism. So such stereoisomers which have same chemical properties, almost structurally also similar, but differ only in one property, that is rotation of plane polarized light. If rotation of plane polarized light is different by two isomers, then they are referred as optical isomers. And usually optical isomers must be non-superimposable mirror images. They form non-superimposable mirror images just like our hands. Two hands are non-superimposable mirror images. I have removed my hand, and its mirror image, if you want to see, it will be this one. So when I try to bring this one onto this one, it is what? Non-superimposable, and this is referred as chirality. What chirality means is that it is handedness. So that's chiral. And if these non-superimposable mirror images lacks SN axis of symmetry, then they may result in what? Optical isomers. So here in this case also, in complexes also, you just have a look at. We have tetrahedral complexes and octahedral complexes which exhibit optical isomerism. Even very few cases of square planar complexes also is a rarity. They are also exhibiting what? Optical isomerism, but there's some exception will be there. Your ligand has to be what? Chiral, not the complex is as a whole. It results in the complex being chiral. But usually optical isomerism arises in tetrahedral complexes and octahedral complexes only. There is some exceptions in the case of square planar complexes. Most commonly, we come across optical isomerism in tetrahedral and square planar complexes. Just like in your carbon compounds, where any four different groups around carbon will result in what? Optical rotation, chirality, and its mirror image will rotate the plane of the polarized light in opposite direction. That where if four different ligands are bound to central metal atom, a phenomena that is unsymmetric nature will creep in. If it is unsymmetric, then what is possible? Optical rotation is possible. So see, in the case of iron with four different coordination bonds, with one with cyclopentadienyl, another with carbonyl, another with acyl, another with triphenyl phosphine, making that one as cyclopentadienyl iron phosphine acetyl carbonyl complex. Cyclopentadienyl iron phosphine acetyl carbonyl complex. So here its mirror image, both are referred as, you just go for writing it in any form. As it is tetrahedral, retain the geometry and write its mirror image, both will form what? Optical isomers. Another example with beryllium, bis benzoyl acetonato beryllium complex, bis benzoyl acetonato beryllium complex. So benzoyl is C6H5CO, acetonato is CH3C double bond O CH CH3CO CH, that is acetonato. CH2, that is bonded to benzoyl. So your bis benzoyl acetonato beryllium complex exhibits what? Optical isomerism. Optical isomerism, that it is disymmetric molecule. This is a disymmetric molecule. So it results in what? Optical isomerism. Optical isomerism in octahedral complexes with MAA2B2 type of ligands. AA is a bidentate ligand and B is a different ligand from A. So in total, the coordination number is 6 here. Example, COEN taken twice Cl2. COEN taken twice Cl2 plus ion. In that, you can write cis form and trans form, but the trans form do not exhibit optical isomerism. Only the cis form exhibits optical isomerism. Cis form, where two chlorines are close to each other with 90 degrees of separation, and its mirror image if you could write, then they result in optical isomers. By simply looking at the molecule, we may not be able to answer whether it is optical isomer or not, but experimentally it is evident that this is a optical isomer where it rotates what? Plane polarized light either in right hand direction or left hand side, either it towards dextro or towards a levo. One will become dextro and another will become levo complex, and its transform is not optical isomer, that it is not rotating plane polarized light, that we should keep it in mind. Okay, then comes up with another type of complex where it is MAA3 complex. The same type of ligands, bidentate ligand, bidentate ligand with ethylene diamine. We can choose with cobalt plus 3, cobalt plus 3. So here it is plus 3. This complex also exhibits optical rotation. You just try to write the mirror images of each other. The mirror images of each other will produce dextro and levo isomers, which are optical isomers. Okay, so with that we have seen optical isomers in octahedral complexes and tetrahedral complexes, and geometrical isomers in square planar and octahedral complexes. That's isomerism in the case of stereoisomerism in the case of octahedral, square planar and tetrahedral complexes. Hope you understood, and keep following the lectures. Thank you.